A star's life ends with a brief, volatile transition known as the Planetary Nebula phase. This period lasts only tens of thousands of years, a fleeting moment on cosmic timescales, where a dying star ejects its outer layers into space. Historic observations at optical wavelengths portrayed these nebulae as simple, isotropic spheres of glowing, ionized gas. We understood them as relatively uniform, expanding husks. Recent near- and mid-infrared observations from the James Webb Space Telescope reveal a highly complex fractal architecture hidden beneath that gas. These environments are defined by extreme physical parameters. Located 4,000 light-years away, these structures are shaped by stellar winds exceeding 1,000 kilometers per second and core temperatures over 20,000 Kelvin. Relying strictly on optical wavelengths masks the true nature of these systems, which function as highly structured engines driven by binary interaction. To build a model of these engines, we rely on two distinct targets: the structural mapping of NGC 6537, the Red Spider Nebula, and the spectral data of NGC 6302, the Butterfly Nebula. The data suggests a specific thesis. The macroscopic physical structure of the nebula actively forces the surrounding material to create its own microscopic chemical environment. This solves a persistent paradox. We must explain how fragile molecular ices survive extreme ultraviolet irradiation while positioned fractions of a light year from a superheated stellar core. Proving this connection would establish planetary nebulae as active chemical factories rather than dead stellar remains. Standard isotropic winds expand equally in all directions. However, NGC 6537 features constrained bipolar lobes, indicating the outflow is being mechanically directed. This thermal map identifies the mechanical constraints. The dense red central region pinches the nebula into a narrow waist. Inside that core, an elongated S shape marks the exact points where high-velocity matter collided with the shell. This S shape marks the collision between a fast-moving jet and previously ejected material, sculpting the rippling structure we see today. Radiating along the outer lobes are hairy filaments emitting heavily from molecular hydrogen. These filaments are the result of non-continuous mass transfer. A hidden companion star orbiting the primary core physically interrupts the gas outflow, causing it to fragment into rhythmic waves. The macroscopic architecture is dictated by these mechanical constraints. Binary interaction creates a dense circumstellar torus, and that torus shapes the resulting nebula. This photograph shows the core of NGC 6302. A dark torus bisects the lobes, obscuring a central star that burns at 220,000 Kelvin, radiating intense ultraviolet energy. This creates a paradox. Thermal energy of this magnitude should trigger immediate photodissociation, destroying any complex molecules in the vicinity. However, JWST observations detect a rich surviving chemistry, including reactive methyl cations and polycyclic aromatic hydrocarbons. High spatial resolution mapping of the torus provides the solution. The density of the torus acts as a localized shield. Within the torus, light extinction reaches a magnitude of AV greater than 76. This density is sufficient to completely block incoming ultraviolet radiation. This dense physical shielding creates a localized deep freeze, perfectly isolating these fragile molecular structures from the star's otherwise lethal radiation field. This chart shows JWST MIRI data targeting CO2 gas. The sharp blue absorption peak at 14.98 micrometers confirms the molecule's presence. However, identifying this signal is difficult because it is buried behind a chaotic layer of spectral noise. This graph compares observations with a model of crystalline silicate. The orange curve shows how this dust contaminates the data. To isolate the CO2, we mathematically fit this dust continuum and divide it out, noticing the gap between the lines. These stacked graphs show the isolated target data after removing that dust continuum. Between 15.2 and 15.3 micrometers, we see a distinct double peak structure. Comparing this shape to the laboratory samples below reveals a perfect match. This specific spectral fingerprint is the definitive signature of pure, crystalline carbon dioxide ice. Carbon dioxide ice sublimates into gas at temperatures above 70 to 90 Kelvin. Yet this ice maintains cryogenic stability while located fractionally away from a 220,000 Kelvin core. The torus functions as a cold envelope, similar to a young stellar object. The macroscopic shielding allows for cryogenic temperatures in a superheated system. Merging the binary jet dynamics of NGC 6537 with the shielded torus of NGC 6302 creates a cohesive, predictive model for planetary nebulae. The data shows a gas-to-ice ratio that is an order of magnitude higher than in typical young star-forming regions. This ratio suggests that CO2 formed in the gas phase during the earlier AGB stage, freezing onto dust grains only after the binary interactions built the torus and lowered the local temperature. Once frozen, CO2 ice serves as a physical anchor. It facilitates the surface chemistry required to build complex organics like formic acid and acetaldehyde. This structural integrity is temporary. As the nebula expands over millennia, the torus begins to degrade. As the shield fails, the ices sublimate, releasing these sheltered organic materials back into the interstellar medium. These complex molecules eventually incorporate into the formation of new star systems. Planetary nebulae function as dynamic, shielded incubators, responsible for enriching the universe with the complex organic materials necessary for life.